There we go. Finally got it to work.
Oh my gosh.
Okay. All right. Everyone can hear me good on Zoom?
Yes.
Awesome. I guess we'll go ahead and get started. So her lecture today was just review, so that's pretty much what we're going to do. Just finish the test prep, so no reason to go over the lecture notes. So we'll just hop right into the test prep where we left off. So if you remember on Thursday, and if you didn't see it, there's the website, or on the website is the video where we went over it. But we talked about Arrhenius, Bronsted, Lowry, Lewis definitions for bases and acids, identified 6 strong acids and 6 strong bases, pH scale, kind of the baseline for KW, which is used a lot in our acids and bases problems, the salt, pH of acids and bases, and kind of did the basic stuff. And now we'll be moving on to kind of the harder stuff, the problems that she'll expect you to do whenever you take your test on Wednesday. So we're going to start by solving for the pH of a base. And you know it's a base because it's NO2. And if we look back on our bases from way up here, it was NO2. And we look here, it's not a strong base. So we know it's a weak base. And we also know it's a weak base because it has a KB. And strong bases won't have KBs because they ionize completely. So we know we're solving for a weak base. And base, you also know because of the B for the K. And so how do we start this? So the test prep key and the test prep are both on the website. So I have the key here and that to go off of. So let me go down here. And which one was it? It's right here. Okay. So the way you want to start it is to set up your formula. And I'm just going to cheat and use this. Okay. So we have NO2 plus H2O. And that is reaching equilibrium. Remember, equilibrium is the double arrow that I can't make on the computer, but that's the best I can do. With OH, and these will have the negatives, plus HNO2, which is the conjugate acid of NO2. Okay, so we know that. And what was the next step? It's to start at T equal to 0. Move that out of the way a bit more. At T is equal to 0, what do we know? We know that we have 0.25 molar of NO2. And we know that H2O is a liquid, so it's going to be dropped out of the formula. So we don't need to worry about anything there. And we know at T equals 0, the reaction hasn't started yet, so OH is 0 and HNO2 is 0. And then whenever we reach equilibrium, we need to know what 0.25 minus X is. And that X is going to be what these are. Correct. Okay. And so where do we need to go from here? Well, we need to write our KB equation. So KB is equal to products over reactants. So we know it's X squared from the 2 X's right here. And we divide it by the reactant, 0.25 minus X. And remember that water is being dropped out, so we don't have to worry about anything there. All right, so then we need to find out if we're able to drop this X in the bottom, because that makes your problem go a lot easier. So does anyone remember the way to do that? to check to see if you can drop your X?
No.
Let's look here. Did you do it on here?
It doesn't have anything to do with the quadratic formula, does it?
Not do it on here. Okay. The way to do that was to shoot. I don't even remember. There's a formula that you use to see if you can skip your X or drop the X. And I can't remember what it was. I just completely mind blanked. But so let's just
if
go ahead and
this
shoot
is
for this
any-
problem that we don't need the X.
If
because
this is any
most-
consolation,
Oh,
she
yeah. Go.
said on the exam there wouldn't be any questions
Oh,
that would need the quadratic equation.
okay. Well, there you go. So you don't need to worry about it. So if that's the case, then we know we can drop that X because that is what results in the quadratic equation. So then that simplifies our equation to just X squared divided by 0.25. And we already know the value of KB is 2.2 times 10 to the negative 11th. And we know that's equal to X squared divided by 0.25. So then it just becomes a simple solve the equation. You multiply both sides by 0.25. Okay, and you get 5.5 times 10 to the negative 12th is equal to X squared. And then you just take the square root. And you get 2.34. Yep, right there. 2.35. 2.35 times 10 to the, 2.35 times 10 to the negative 6th. And then how do we get pH from that? Because we have X, that's the value of X. So what do we need to do to get pH?
Wouldn't we solve for POH first and then that's subtracted by 14?
That's exactly what we do. So what's the equation to solve for pOH?
Negative log of OH.
Yeah, that's exactly right. Negative log of 2.35. I'm just going to go ahead and use the E. Do y'all know what that means? Whenever you put E like that?
Exponent?
Yeah. So I'm just going to go ahead and do that. Instead of typing out the times 10 to the negative 6 and everything, I'm just going to do E negative 6. It'll make everything go a lot quicker. So we take the negative log of that. Where's my log? Answer. And we get 5.6298. And if we use our sig figs rules, we have 3 sig figs. So we need to go 3 decimals. Oh, wait, actually, we're not supposed to have 3 sig figs. There we go. So we have 2 sig figs, so we need to go 2 decimals. So 5.63, and that's equal to our POH. And then so we just do 14 minus 5.63. Oh, yeah, you're right, my bad. Yeah, 2.4 times 10, negative 6. Log of that still comes out to 5.62. So 5.62. 14 minus 5.62 is equal to 8.38. And we know we started with a base and our pH is higher than 7. So we know we're in the right ballpark, and that's the way we check our answer. And that is equal to the pH. And that's how you solve for that. So we'll move on to.
If you don't mind me asking,
Yeah.
how did you know how to write out that reaction?
The reaction, I'm not, most of
I get
A
confused.
lot of
On,
people ask me that. I just used this for that one, but the way to figure them out is to just use Newton. It'll walk you through kind of a whole bunch of them. And that's how I learned when I was in her class. But it really just comes down to studying and memorizing how reactions work. But a little kind of a cheat sheet. Whenever you have a base, it's going to it's going to react with water all the time. You're going to have base plus water. And then you just solve for the rest of the equation. So if we know we have NO2 and H2O, because it's going to react with water, then we know one of those H's is going to come to the NO2 and make the NO2, and that's going to leave an OH. So
Okay, and this is
start by
kind of
knowing that
just
it reacts with water.
okay. And is that kind of the same thing with acids?
I think we're about to solve one of those, and let me check here real quick before I say anything. Looks like, oh, this is a different. Oh, okay, that one won't work for that. I believe it is. Hold on. So let's say we had, let me do it real quick. Let's say we had HCl, or no, we need a weak acid. What is acetic acid? It is CH3CO2. Trying to find a weak acid formula. HCO2, H2CO2. We'll use that one. Okay, so if we have H2CO2, then we react it with water, H2O. What do we get? There we go. One of the H's would go across, so it would make H3CO2 and plus goodness, OH. Let me see what happens there. H3CO2. Sorry, this is all just top of my head. CO2 plus H. Okay. So it would make, this is what happens with acids. It makes, so you have H2CO2, which is a weak acid, plus water, and that makes CO2. So it takes these two hydrogens off and adds them to, that's not right. H3CO2 plus H2O. That's not balanced. Good Lord. Okay, we'll figure it out when it comes to it.
Okay.
But just because I can't
that's
really do
kind
it
of
on
one
the
of the
fly
things
very
that
well.
throws me off.
But yeah, so for a base, you will be adding it to water, and it makes an OH and a basically the base plus a hydrogen. So if you have this, then it makes an OH plus.
And
And
that
then-
would be the conjugate, right?
Yeah, this is the conjugate acid.
Okay. Thank you.
Okay, so now let's move on to the next one. Calculate the pH of a 0.45 molar sodium nitrate solution for HNO2, Ka equals 4 times 10 to the negative fourth. So this is the one where you're given a base and you're given the Ka. And remember, the Ka is for an acid, so we can't necessarily use it. So what we need to do, I believe it should be on here. Where is it? There it is. Yeah, what we need to do is use that Kb equals Kw over Ka formula. But first we'll start with the basic formula, NaNO2. And that is becoming Na plus and NO2. Na positive ions plus Oh, wait a minute. I think this is a strong base. Or strong. Why is it doing that then? I think it's a strong base because it's disassociating completely. But let me solve it real quick. NaNO2. NaNO2. Sodium nitrite. And is it a weak or basic? But is it strong or weak? Oh my goodness. Sorry. Let's go back to this. Okay. Oh, okay. I was right. Oh, okay. Sorry. There we go. Na plus NO2 negative. There we go. Okay. So that's the dissociating part. And then this is your base or your what you use to solve the problem. So you go down and you make the new formula NO2. There we go. Plus H2O. And that's the one that goes back and forth with, so let's solve without looking, it would be HNO2 plus OH, because one of those H's goes here and one of them stays behind. Just like that. Yep. Okay. And then we know, let's move it down. We know at T equals 0, NO2 is going to be 0.45. 0.45 molar. We know the water will drop out. So we come over here. HNO2 is going to be 0. And OH is also going to be 0. Correct. And then we know 0.45 minus X and X and X. And we have the Ka, but we need the Kb. So we're going to do Kb is equal to Kw divided by Ka. And we know Kw is equal to 1.0 times 10 to the negative 14th. So 1.0 times E negative 14 divided by 4.0 E negative 4. And if you do that in your calculator, you get 2.5 times 10 to the negative 11th. So 2.5 E negative 11 is equal to Kb. And so then you plug that into your final equation. Kb is equal to X squared divided by 0.45 because, like she said, you know the X is going to drop out. So you don't need to use quadratic formula. So you know it's just going to be X squared divided by 0.45. And let's copy paste this for Kb. And then we just do the math to get 2.5 times 4.5. X is equal to 3.35 times 10 E negative 6. And that's equal to your, if you look right here, that's equal to your OH. So again, you have to do that, solve for POH and then solve for pH. So if you take the negative log of 3.35 times 10 to the negative 6, 3.35 times 10 to the negative 6.
How come it's 3.35 instead of 3.4?
You are correct. I bet. I was never a good good with sig figs. Times 10 to the negative 6. Then you take the log. And you get 5.47. Yeah, because you have 2. Oh, no. Yeah, you have 2 sig figs, so 2 decimal points. And that's equal to your POH. And then you just subtract from 14. 14 minus 5.47 is equal to 8.53. Let me check that with the key. 8.53. There we go. And that's how you get your pH. So it's basically the same exact steps. The only thing you have to do is if you have a base and you are given Ka, you need to solve for Kb from Ka and Kw. And remember, Kw is that number you have to memorize, that 1 times 10 to the negative 14th. So that's just showing you how to solve for Kb from Ka. And then, so now we're moving on to a buffer problem. Buffers are for pH. If you have 8.53, or if you're taking the negative log of 3.4, that has 2 sig figs in it. So whenever you get your answer, it's 5.4685. You have 2 sig figs, so you need to go to that number of decimals. So if you had 3 sig figs, then you would need to go to 3 decimals. Most of the time you'll go to 2 sig figs, or 2 decimal places on pH, but not every time. She might throw in one to trip you up. Got it? All right, so now we're on a buffer. And if you remember buffer, she's not always going to say the pH of a buffer. Sometimes it'll just say, calculate the pH of a mixture containing this and this. And the way to know it's a buffer problem specifically is because of that and. Any problem that says and like that is always going to be a buffer problem. And so when you know that, you kind of already are halfway done to solving the problem. So let's go to here. Let's widen it out a little bit. Okay, buffer pH. So the first thing we need to do is we need to label this as a weak base. The NH3 is a weak base. And then the NH4Cl is going to be another weak base. That might be an acid, actually. It doesn't matter. Because what we need to do, I think this is out of order. I think it worked over here, and then I moved over here. Let me read over this real quick. Okay, so you're solving for buffer pH. And remember, if you're on an exam and you put that you're solving for a buffer problem, she's going to give you usually an extra point if you describe what type of problem you're working on. Just a thing she does to help you out. So make sure when you're on your exam to do something like that every time. And then let's see. This is way out of whack. So you're given the Ka. Okay, so that's one step. You're given the Ka and you need the Kb. So let's go ahead and solve for that. Kb is equal to Kw divided by Ka. And then so 1.0, it's on here, I might as well use it. So Kw divided by Ka, and that's equal to 1.8 times 10 times 10 to the negative, was it fifth? Fifth. Okay. And that's just using the 1.0 times 10 to the negative 14th divided by the Ka you're given to get that. And then POH equals PKB plus log. Oh, this is, she's using, that's why I was confused. She's using the equation, I can't remember the name of it. Hold on one second. Let me look it up. Equation for buffers. Henderson-Hasselbalch equation. Okay, so the way I did it was always different. I always just went the full other way, but we'll use the Henderson-Hasselbalch to solve for this. So this is an equation you can remember, and it'll work on every buffer problem. So what you want to know is your POH is equal to your PKB, what was the rest? Plus the log of HB plus divided by B. HB plus divided by B. Okay. And I know that looks confusing, but we'll work through it. So we know the PKB, or we know the KB is this number. So then you take the negative log of that, log of 1.8 times 10. Oh my goodness. Log of 1.8 times 10 to the negative fifth. And you get the PKB is equal to 4.74. She actually dropped a, oh wait, is it 4.75? No, it's supposed to be 4.74. Plus the log of the two molarities. Plus the log of, and you start with your HB, and then you move on to your B. So that one, and then you move on to this one. Okay, so 0.20 divided by 0.24. Do y'all remember learning about the Henderson-Hasselbalch equation in class? She covered it for just a little bit. I don't remember if.
Yeah, she went over it
Yeah.
a little bit today in
Okay.
the review.
What was that?
She went over it today in the review.
Okay. All right. Do y'all feel more comfortable with the Henderson-Hasselbalch or with solving it like a regular acid base? Regular?
Could we do both?
Yes.
So that we
I
could-
don't have the notes prepared, but I might be able to work through it real quick.
Okay, because is the Hender-Hassel equation, like, is that guaranteed to work whenever we're given a buffer solution like this?
Yeah, the Henderson-Hasselbalch is specifically meant for buffers. So if you're given a buffer solution, oh, I messed this up. I didn't even notice that. Oh, no, I didn't. Okay, sorry. Yeah, the Henderson-Hasselbalch equation will always work on buffers. Because on this one, you're given the Ka, so you need to solve for the Kb in order to plug it in. But you're always given all three of these values, the K, either the Ka or the Kb, and then your two molarities. And so you just plug it in to get the answer.
Okay.
But we can try and work through it the regular way as well, that you do acids and bases. That's the way I would always do it whenever I was in her class.
Do we have the full hour for this SAS session?
We have 9 more minutes, but I can because the Zoom is still messed up, but I can redo the Zoom and then repost it to the chat. So we can just hop in another one.
Thank you.
Yeah. So what do we do? So then we just solve the equation. So 0.2 divided by 0.24. Then you take the log of that. And that's equal to 4.74 plus 0.079. Yeah, 0.079. And then technically it would be 0.0. Yeah, there it goes. 0.08, but for the sake of this, we're just going to do that. 4.74 plus 0.079 is, oh, I'm sorry, this is negative, not plus. I'm so used to doing negative log. That would be 4.74 plus that is equal to 4.660. And then we look back here. Easiest way to do that is you count the sig figs up here and then do that for down here. Use that rule. If you get a little lost in down in all this, but I think, yeah, that's equal to your POH. OH. And then you just subtract that from 14, 4.66. And you get 9.34 as your pH. And if you see here, she got 9.33, I got 9.34. She's never going to count you wrong for getting it 0.01 off. She knows it's just rounding error, so you don't have to worry about that as long as it's, you did everything right and you got to the same answer. And then we'll move on to, or do y'all want to go over how to solve it regular? Okay.
I think it's fine if we continue forward. I just kind of want to throw that in there just in case.
Let's take a quick vote. So I can
I'm
do
good.
what the majority wants.
I'm good with the one you worked.
So am I.
Okay. As long as you can memorize this part right here, POH is equal to PKB plus the log of HP plus and B. As long as you remember that part, go home tonight and tomorrow and just read that over a few times. Then anytime you get a buffer, you can solve it. All right, so what happens if you add a small amount of a strong acid or a strong acid or a strong base to a buffer? This one's on y'all. Y'all remember what a buffer does?
Wouldn't it equal it out, or not equal it out, but the reaction change to equal out? I guess, yeah, equal out the products and reactants.
Yeah, that's one way to describe it. I think I know what you're trying to say. So if you add a small amount of a strong acid to a buffer, so let's say we have, I don't know any equations of a buffer, so never mind. But if you add a small amount of a strong acid, then what it's going to do, that buffer is going to take it in and react with it without changing the pH. So it's only going to, an acid will lower the pH, but only slightly. And then the base will raise the pH, but only slightly. The main thing to know is just it's only going to slightly change the pH. And that's what y'all did in titrations. Whenever you have the buffer solution and then you're slowly adding stuff to it, you're adding hydrochloric acid, but it's barely changing the pH because that's what a buffer is meant to do. All right, so now we need to estimate the molar solubility of silver chromate in pure water if the solubility product constant for silver chromate is 1.1 times 10 to the negative 12th. Okay, so all we're given here is the solubility product constant. So let's go to here, solubility product constant. Oh yeah, this is a KSP problem. God, I hated these. KSP, that's your solubility product constant. And if we go here, yeah. Okay, so this one is fun. Talk about knowing equations. Ag2 CrO4. It's going back and forth and okay. So whenever you're given a problem like this, where it's asking for the KSP and it's saying you're putting this into pure water, what's going to happen is it's going to disassociate. So that one, there. And it's going to disassociate into 2 silver ions plus 1 chromate ion. See, it just basically splits it right in the middle. You have this and you split it in half and that's dissociating. But since you have 2 silvers, you got to make sure to put that 2 in front of the silver. The CrO4 is considered 1 ion. So it's not 4 oxygens and 1 chromium. It's 1 CrO4. And then you remember it goes into the X's, which is not fun. So it's 2x because you have 2 moles. And then it's a singular X for the chromate. And then remember, this is where you do the 2x squared in the formula. And then it's multiplied by X. Does she have like that full formula? Yeah, okay. So your KSP is equal to the 2 ions multiplied by each other. So Ag and then CrO4. And since you have the 2 here, this gets squared. That. And so that's how we resulted in this. Kind of working it backwards right now, sorry. There we go. And then from there we do, we square the 2x. And if you remember, when you square it, it becomes 4 because you square the 2, and then you also square the x. So it's 4x squared. And then you're still multiplying that by another x from right here. So it becomes 4x cubed. There we go. And then all you have to do is take your KSP right there, plug it in for where KSP is. I'm going to go ahead and put KSP here. And then, what did I do? There we go. And then divide both sides by 4 and take the cube root to clear out the x. So you're left with x is equal to, what was the value? 6.5 times 10 to the negative 5th e negative 5. And that is your answer for the molar solubility of silver chromate. Is anyone a little confused on that? I know I probably didn't explain that the best I could.
No, that's pretty clear for
All right,
KSP.
Awesome. Calculate. Oh, okay. And then we only have 1:30. Is there another? Yeah, we'll answer this real quick. So what effect does adding a common ion have on solubility? Okay. Does anyone remember? So that's what this is asking for. Because you're mixing silver chromate into sodium chromate. So is it going to be more or less soluble if you take your silver chromate and put it in another solution that also contains chromate? Less.
Wouldn't it be more soluble?
No, it would be less. And a good way to think about that is if you had, let's say you had really sugary tea, you have really sweet tea, put like sweet tea, and then you try and add more sugar to it. Are you going to be able to put a lot more sugar into it, or is it going to take a little bit of sugar and then the rest is going to fall out of solution?
Okay. Yeah, I see it now.
Yeah. So just kind of think of that whenever. The meeting's about to end, so I'm going to post the next code in the chat, and I'll see you all in probably about like 2 minutes.
Okay.
All right. Sounds good. Just close it.